Hi there, it's time to resume our discussion of expression evaluation in MonetDB. Okay, before we do that, let's take 1 minute to have a resume, a very brief summary of what we've learned so far about the evaluation of expressions in PostgreSQL versus MonetDB. We found two quite different scenarios there, and this slide is just here to remind you that there is quite a number of differences that we found. For example, the very high flexibility of the expression interpreter in PostgreSQL that was using branches to react to a number of possibilities like nullness, particular types, or the particular position of a field in a row, all of these degrees of freedom that have an impact at runtime, because we have to have branches and decisions that are being made during runtime. All these degrees of freedom go away with the MonetDB approach, in which there are only buts of 2 columns all the time. Actually, one column is the head column is always void, these virtual OIDs. Only the tail column carries values, and we will produce particularly typed, particularly geared and specifically generated versions of our routines, of the butcalc subroutine, for example, that we've seen in the last video, that is specialized to run only over buts that have a long tail or a byte tail or an integer tail. All of these are super specialized, and there are less degree of freedom. That means less branches, less decision at runtime. This leads to very tight code, very tight loops that contain very few instructions only. So what we see is instruction locality. The few instructions, maybe only a handful of instructions inside these tight loops, they fit in even the tiniest instruction cache of your modern CPUs. So the CPUs will find all the necessary instructions for loop processing always in the cache. No cache misses, super efficient. It's different on the PostgreSQL side of things, where we have long code paths that are distributed over many functions and many more instructions that you will probably find in the instruction caches of your CPU, many more cache misses there. This can lead to further inefficiencies. I'm sorry about that. The tight loops are actually highly optimizable by modern compilers, and we will look at this one particular optimization here, the so-called loop unrolling, that is super important to have really high performant tight loop code in modern CPUs, and we will see why in just a few minutes in this video. This is something that we will look at now. We will also look at data parallelism, which is another source of efficient optimization in modern CPUs. And this is something that's also not available on the PostgreSQL side of things, because there's really little source of parallelism. All we do is row by row interpretation of expressions, and there is really little opportunity, little potential for parallel evaluation, or the evaluation of the same expression for multiple rows at once, for example. This is easily performed on the MonetDB side of things, and the next video will talk about just that. There's one plus point here, I would say, for the PostgreSQL side of things, and that's the row by row result generation. So whenever we have produced the intermediate result for just a single row, that row has been entirely processed and could be passed on to other operations in our query plan. It's different on the MonetDB side of things, where we would fully materialize all intermediate results of all arithmetic expressions, or scalar expression that might be computed in a larger complex expression. All of these intermediate expressions would be held in their own buts. We would need to find place, actually memory space, to hold all these buts. Many intermediate results, each of these may be 1 million of entries long. This might lead to some substantial space that needs to be available in in memory, and that could really lead to a severe bottleneck for MongoDB. All right. But first, let's have a look at the really efficient code that modern compilers can generate for the tight loops that we find inside routines, just like bat-calc-sub. And to remind you of the internals of bat-calc-sub, I've brought an excerpt of that routine with me. We have seen a more fully fledged routine version of that routine in the last video. This would be the excerpt, the core, the gist of that routine. It's just the bat-calc subroutine that operates over two input vectors, left and right. You see these pointers pointing to entire vectors of integers, and we would generate a vector of results here. That loop would do nothing but actually traversing the input bits, and in parallel also traversing the output bits. So we use the integer indices I, j, k to point into the inputs and into the output. We would iterate over a fixed length of elements in these vectors. You see that I'm assuming a fixed length here, but of course any length would do. And we maintain our indices. So with each iteration, we would advance one row, one element inside the vectors that we are processing. In the actual processing is just this one line here, where we perform the subtraction of right from left and assigning the result of that to the resulting vector. That's all that's left to do here. This is a super tight loop, and as you can imagine, it leads to very few assembly instructions on the side of the CPU. And we can actually see that if we look at the actual native code that is being generated by a modern compiler. I'm doing this here with the help of the Compiler Explorer, which is hosted at godboll.org. Okay. What you can see here, or what you can do here, is actually have two panes side by side. The left-hand side pane would be the C source program pane, where I have just pasted the code, the C code of the bat-calc subroutine that we've just seen on the slide. On the right-hand side, you would see the associated machine code that has been generated by a modern C compiler. In this case, it's version 10 of Clang. Okay. The nice thing is here that you can actually have a correspondence between the instructions on the right hand side. Maybe these instructions here. These three instructions make up the loop body, which is now marked blue on the left hand side. This loop body, these are the instructions, the three CPU instructions that are implementing the loop body of our bat-calc sub super tight loop. The yellow instructions here would be in charge to implement the loop control. So I'm sorry about that. Just the testing whether we have passed the end of the loop or the increment of these counters here. All of this is found in the three yellow marked instructions, native CPU instructions on the right hand side. Okay, as you can see, the entire bat-calc subroutine leads to about 8 CPU instructions on the right hand side. This is super tight and fits into any CPU instruction cache. It's also very efficiently evaluated. And please compare this handful of CPU instructions with the significant longer path of instructions that a PostgreSQL style expression interpreter would have to evaluate. There's actually no comparison between the super tightness of these loops and what a PostgreSQL threaded interpreter style evaluation of expression would face. Much more efficient in this particular case. Okay, so what you can see here is what the Compiler Explorer just showed us for the native code of the bat-calc subroutine. It's just our representation of the same code on the slide here. Okay, let's have a brief look at what happens here. Indeed, what you find is the loop, the tight loop that has to be implemented by the assembly routine, of course, the tight loop that we have specified in the C program. And the tight loop would work with a loop index that's stored in the CPU register AX. Okay, so this XOR operation would just zero out AX, and as you can see here, we would use the AX register to actually implement and represent all the three loop counters I, J, and K that we have used in the C program. They are all mapped to the same CPU register. Okay, so And then the body of the tight loop would just start. We would load the current element of the left input vector pointed to by the register RDI at offset AX. We would load 4 bytes, a long word, so 4 bytes, and move that into register ECX. We would then subtract from that the corresponding element of the right hand side vector, okay, at the same index. And the result of that subtraction would land again into ECX. You see that on the right hand side I have sketched the semantics of the machine instruction that you've seen here, that you're seeing here on the left hand side. Okay, so one subtraction would have been performed, and now it would be time to just place the result of that subtraction, namely held in the ECX register, and save that into the result register in the RDX register here. Okay. Having done that, we would just proceed and increment our loop counter, and that's what's being done in this particular line. And once we've done that, we are ready to enter loop testing. Shall we exit the loop? And only if Rx, the AX value in that register, would exceed 1024, the number of elements that we wanted to process, if you recall from the C program, only if we exceed this particular value, we would exit the loop. If the condition is not true, if we are not exceeding 1024, we would just resume the loop and start over again. So that's a quite literal, quite obvious, straightforward implementation of the loop that we have just seen in the C program. That's what's happening on the side of the CPU, and it's only 8 instructions. Okay, great. The only thing that may be worrying here, that this routine invests as much instructions for the loop control, those marked now, as it does for the loop body. This is the useful work we are aiming to do, namely the subtraction of the elements in the 2 input bus. Okay, so lots of loop control for the same amount of useful work that we are trying to do here. Okay, 1 loop exit test per element, per error element, per subtraction performed here. And that's something that's not ideal. We would like to increase the ratio of useful work over the loop control that we are doing. And that's an idea that's known as loop unrolling. Do more useful work inside the loop body and do less loop control. Okay, that's actually a very simple idea, and it's sketched on the next slide. So that would be the a C implementation of the loop unrolling idea. We would manually perform the loop unrolling here and would not rely on a compiler to do that for us. A modern compiler would perform the loop unrolling for us, but to display the basic idea, we could just do it manually, and that's what's being done in the variant of the bulk calc subroutine that you're seeing on this slide. Okay, so let's see what's going on here. Let's increase the pointer size actually. Can we do that? Okay, great. So you see that the whole setup is the same, left and right input vectors, result vector, indices I, J, K. All right, but now as you can see, we would increase the indices here by 4 in each loop iteration. It's our intent, whenever we enter the loop here, the tight loop, that we actually performs 4 subtractions. 4 subtractions, the subtraction of 4 elements that are adjacent in the left and right input vectors. And that's what you can see here. We would, of course, perform the subtraction of the elements at indices I and J, which are in sync. But we would also perform the subtraction for the 3 following elements, immediately following elements in the left and right vectors. So that would be the useful work that we are trying to do here. And as the comment here on the right hand side implies, this is independent useful work. The first subtraction, the second, third and last subtraction, they could actually be performed in parallel. It's super obvious that there are no data dependencies between these, and a good compiler would be able to schedule the variation of all of these subtractions in parallel and have them performed at the same time for us. Okay, this is not the focus currently, the parallelism, but what we also see is that now only after we have done 4 useful units of operation, namely subtraction, that's what we are after here, only then, only after 4 of these subtractions, we would then consider again loop control and try to decide whether we have to leave or exit the loop here. Okay, so the ratio of useful work over loop control should be better by a factor of 4 actually. We have to be a bit careful because this routine will only work correctly if the size that we are considering here is actually divisible by 4 without any residue. But we will come back to that in a minute. I've brought the assembly equivalent of this routine with me, and I can show you on the next slide. The program will be larger, the assembly program will be larger because the C program has grown. Okay, so that would be the unrolled assembly code that actually the compiler would generate for us automatically if we activate this unroll loops compilation switch, an optimization compilation switch that allows or actually asks the compiler to perform this loop unrolling optimization for us in the assembly code. And the idea of loop unrolling that we've just seen on the C side of things is just the same on the assembly level side of things. We would enter a loop that in the overall structure really is the same loop as we've already known. You see that we are still maintaining the loop counters in the AX register, and with each iteration of the AX register we actually increase AX by 4 now, and then see whether we've already reached 1024, the ending condition of our loop. If this is not the case, we would just resume from the beginning of the loop. Okay, now that we increase AX by 4 in each iteration, we will of course only perform 256 loop iterations, a quarter of 1024 here. So we will enter this particular part, the loop control part, only a quarter of times. Less loop control for the same amount of useful work done. Okay, so it's only this would be the loop control, and it would compare with this amount of useful work that is being done inside our loop. What you can see here is just loading the left operand into the ECX register, performing the subtraction and storing back the result into the resulting vector. And we have seen that already. The same things, the same group of operations, the same 3 instruction group of operations is being performed for the next element in the vectors. And you can see that this next element in the vectors is being accessed using this offset of 4 here. So with an offset of 4 bytes, we reach into the input and into the output vector. And this is because we are processing 4-byte wide integers, this would just correspond to an access to the subsequent element. And we do the same at offsets 8 and at offsets 12, so that we process the element at offset 0, at offset 4, offset 8, and offset 12. These are the 4 adjacent elements in the input and output vectors. All are being considered in the same loop. Only then we would enter loop control again. And there is really something to be saved here. There's real runtime to be saved with this loop unrolling optimization. Let's switch over to a C program that I've brought with me to demonstrate just that. It would be a C program to demonstrate the effect of loop unrolling. In this case, again, because we are on the level of C, of manual loop unrolling that I have performed myself. The usual setup here, you see that we will iterate over quite a number of elements. It's 256 million of elements that we will iterate over. Okay, so a substantial number of elements. And that would be the original BATcalc subroutine, which does not contain loop unrolling. So for each loop control that we are performing here, one subtraction operation that is being performed. That would be the original BATcalc subroutine. The BATcalc sub unrolled routine would be this. and we have seen it already on the slides. So loop control here, we are advancing by 4, and the useful work here, we are performing 4 subtractions in each loop iteration. Okay, so that would be the 2 routines. Then there's only the main program that would just fill the input and resulting vector. It would allocate them and then fill them, but this is no real importance here. And then there is a switch. There's a command line switch, the -u switch. If I activate that switch, we will actually invoke the unrolled version of the routine. If I do not specify that switch, we will measure the original, the vanilla version of the routine without loop unrolling. So let's see whether we can indeed see some performance difference there. So let's see, let's just invoke the compiler for this unroll program. All right, compiled. And then let's run the program a number of times, like 5 times, let's say, first without unrolling activated. These 5 times will allow us to compare running times and have a notion of an average running time that we have to expect. So it's 460,000, I would say, microseconds here. And now let's enable the unrolling and perform the 5 measurements again. Let's go. All right. Oh, that looks better. Oh, okay, so around 400,000, I would say. Okay, so that's an improvement already. So that would be the effect of loop unrolling. So some gains that we can have there by performing less loop control, but more useful work inside our loops. Okay. Of course, there is the problem here with this particular routine. As you can see, and as we already mentioned on the slides, this would only work correctly if our size is indeed divisible by 4. So this is an assumption that is being made by this particular routine. We are advancing now loop counters by 4 in each iteration, and of course that would not be compatible with all arbitrary loop sizes or loop iteration counts that we are trying to perform here. And this is, I think, the right time to display a nice trick that has been invented like almost 40 years ago by Tom Dove. And the trick is called, after Tom Dove, it's called Dove's device. This is a nice trick that has been devised that will allow you to use the technique of loop unrolling and still have a routine that is able and capable of processing any number of loop iterations, any number of loop counts, not those that are just divisible by 4, or in this particular example file as divisible if they are divisible by 8. You see, that is a simple loop that has been specified by Tom Dove here, and it's a loop that has been unrolled 8 times for performance reasons. It's actually a copy loop that reads integers from the from array, or the from vector, and stores them in the to vector. Okay, so and to really have some effect from loop unrolling, we would perform 8 of such copies, and then only then have loop control. You see this do while loop that I'm using here. As long as n is still larger than 0, there's still stuff to copy, and we would return to the beginning of the loop to enter the next copy round. So that we enter the loop the correct number of times, we would first divide the number of integers that are to be copied, the count, which is the argument to the send routine, by 8, because each of these iterations will indeed copy 8 of these integers. And as you can easily see, this would only be correct if the count is indeed divisible by 8. This integer division of count by 8 would just remove all fractional parts of the division result. And as this is the case, actually this send routine would do a little bit, it would miss some work in the last few bytes. Last few integers copied might be missed if the count is actually not divisible by 8. Okay. To remedy that, Tom Dove invented Dove's device, which does just this, an unrolled loop copying, an unrolled copying of the from vector to the to vector. It's also unrolled by a factor of 8 here, but Tom had the intent of writing a routine that would work correctly for any count and still would have the gains from loop unrolling. So what you can see here is a little marvel of C language, C programming, C semantics actually. You see that this is a do-while loop, as we have seen before. So this would be the do part, this would be the while part, and we would still resume copying as long as the n here is indeed larger than 0. Okay. And everything is fine so far, but what you can also see is that inside this while loop, you find these case targets. These case targets actually correspond to the switch that is on top of the while loop here. So really marvel at that. This is a do-while loop, and folded into that do-while loop is this particular case statement. And the case statement would look at the fractional part, the residual part of the division of count by 8. Let's assume that the division of count by 8 has leads to a residue of 6. So that would be 6 here. So we would jump into the do-while loop, into the middle of the do-while loop to this particular case branch, and then would perform 6 extra copies of from to, before we then enter the regular while loop, which would do the rest of the unrolled loop copying work. So that switch in the beginning would jump us just into the middle of this particular loop and make sure that we perform first the rest of the work that is not divisible by 8. All right, so this is, I think, a super nice idea by Tom Dove. It really makes me scratch my head when I look at this, and really makes me wonder whether this is legal C at all, and whether C compilers should complain. But it has been looked at closely many times, and nobody found a statement in the C standards that would forbid such a construction, and it actually works in modern C compilers, as you can try out yourself in the dovesdevice.c program that I'm providing for you for download and to play with. As you can see, it's invoking the send routine and the dove send routine, and then it's checking that indeed everything from the from array has indeed been copied to the to array. All right, so if you populate the from array with these 42 literals, then we expect, of course, the to array to carry all of these 42 literals in the end. But if the size is not divisible by 8, and I think I've specified 255 here, which is not divisible by 8, then you will see that the send routine here will do a bit too little, misses some of the copy operations that Tom Dove's device will do perfectly right. So let's play with this to complete this particular video. So let's switch over to our terminal again and compile the whole thing. Dove's device, and run it. And as you can see, indeed Dove's device managed to perfectly copy all of the from array values to the to array, even at the very last few entries of the to array are correctly populated with 42 now, while the send routine missed some of the copying work here. All right, so the best worlds have both of the best worlds. So have a very flexible copying routine that is workable for all possible loop counts, and also have the effect, the very beneficial effect of loop unrolling. Okay, So reduce the amount of loop control work and increase the ratio of useful work done during these tight loops. This is crucial in having high performant loops inside any system, but in MonetDB in particular. Okay, so this is running long again. Sorry for that. Let's bring it to an end. See you in the next video where we will talk about SIMD data parallelism. Bye bye.